This is Brad from UT Dallas, and today we're going to talk about the diode constant voltage drop model. Shown here is a diode, and essentially a diode allows current to flow in one direction and one direction only. And depending on the voltage that is applied across that diode, the diode acts as either a 0.8 volt voltage drop or an open circuit. So when the voltage applied is more than 0.8 volts, the diode acts as a 0.8 volt voltage drop, and when the voltage applied is less than 0.8 volts, the diode acts as an open circuit. So let's apply this model to an actual problem. So in the circuit below, we're asked to find and plot V out versus V in. So we're going to start out with V in equals 0, where both diodes are off. So we have two diodes here, D1 and D2, and they're both off, meaning that they're both acting as open circuits, not allowing any current to flow through them. We can see that there is no grounded part of the circuit that is connected to V in and V out, which means that there's no current flowing from V in. What this means is that there is no current flowing through the 5K resistor at the top, which means there's no voltage drop across that resistor. So therefore, V in equals V out when V in equals 0. Now the question that we have to ask ourselves is, at what point do D1 and D2 turn on? And to find this, we have to consider the voltage drop, or the voltage applied, rather, across D1 and D2 in order to make them turn on. So if we consider D1, there has to be a 0.8 volt voltage drop across D1 in order for it to be on. So let's look at the negative terminal. What is the voltage at the negative terminal of D1? We can see that we have a 5 volt source that then runs through a 5K resistor to ground. Now, since D1 is not on, there's no current flowing through the 5K resistor, so that 5K resistor has a voltage drop of 0. So really we only need to consider the 5 volt source. So what this means is that at the negative terminal of D1 we have 5 volts. Therefore, in order for D1 to be on, the positive terminal of D1 has to be 5 volts plus 0.8, which is 5.8 volts. Now remember, since D1 and D2 are both off still, V out equals V in. So essentially, for D1 to turn on, V in has to be greater than or equal to 5.8 volts. Now let's consider D2. We have another 5 volt voltage source. However, we can see that it's flipped around, so really it's actually a negative 5 volt voltage source. Now remember that D2 had the opposite polarity of D1 as it's facing the other direction. Therefore, we want the voltage drop to be negative 0.8 volts across D2. Therefore, V in has to be negative 5.8 volts or less than that in order for D2 to turn on. So now we've broken our circuit analysis down into 3 different regions. The first region being when V in is greater than 5.8 volts, so D1 is on and D2 is off. The second region being where V in is between 5.8 and negative 5.8 volts, where both diodes are off. And then region 3 being where V in is less than negative 5.8 volts, where D1 is off and D2 is on. So now let's consider each of these regions individually. The first region we'll consider is region 2. So we see that in this region, both diodes are off, so they become open circuits. And we have no current flowing from V in, as none of the terminals are grounded. So current's not flowing, there's no voltage drop across the resistor, and therefore V out equals V in this region. So we can plot this on our V out versus V in graph from negative 5.8 to 5.8 volts. Now we'll consider region 1 where V in is greater than 5.8 volts, which means D1 is on and D2 is off. So D1 becomes a 0.8 volt voltage drop, and D2 becomes an open circuit. Now we can just ignore the right side of the circuit, and we can combine our 0.8 volt voltage source and our 5 volt voltage source into a 5.8 volt voltage source to get this circuit. Finally, instead of having Vin and the 5.8 volt voltage source separately in our circuit, we can just make Vin equal to Vin plus 5.8 volts, simplifying it even further to this. Finally, we can recognize that this is simply a voltage divider with two resistors, and since both resistors are equal, V out is simply the input V in plus 5.8 volts divided by 2, or cut in half. So V out equals quantity V in plus 5.8 volts divided by 2. And we can plot this on our graph as well. Note that the graph is continuous and the slope is 1/2, as V out equals quantity V in plus 5.8 volts divided by 2. Finally, we'll consider region 3, where V in is less than negative 5.8 volts, which makes D1 off and D2 on. So D1 is off, open circuit, D2 becomes a voltage source. And notice that the polarity of the voltage source matches the polarity of the diode. Finally, we can simplify our circuit, ignoring the left part of the circuit and combining our voltage sources into a 5.8 volt voltage source. This polarity causes our Vin to become Vin minus 5.8 volts instead of Vin plus 5.8 volts like in region 1. And we once again have a voltage divider that results in V out equal quantity Vin minus 5.8 volts divided by 2. We add this to our graph. Note that the slope is also the same, m equals 1/2, and the graph is still continuous. And we have our final graph and chart showing each region and V out as a function of V in